First content video, let's go. Talking about limits. We're going to be talking about limits at infinity. Like I said, that means horizontal asymptote. So if you're ever asked to find a horizontal asymptote, find the limit at infinity or the limit at negative infinity. We've also got indeterminate form. Not that I'm worried about anybody on that. L'Hopital's rule seems to be a favorite thing to do for some reason. We've got our composite limits, which don't come up super often, like I said, but they do come up. Intermediate value theorem, which we're going to need to do a good chunk with, and continuity, which is probably going to actually be the bulk of the video because it's got a lot of problems there at the tail end. So let's go ahead and get started. Okay, the big thing with limits at infinity is dominance. So remember, exponential functions beat polynomials and polynomials beat logarithms. If the function on top wins, where are we heading? Good. Person who is screaming at the video for some reason, we're heading to infinity. If the function on bottom wins, that's going to be 0. And if they tie, that's where we're going to take the ratio of the coefficients. So a over b. So like, we'll see in a video, in an example in a second. So let's take this one. We've got the limit as x goes to infinity for square root of 9x to the 4th plus 1 over x squared minus 3x plus 5. Okay, at infinity, is adding 1 really going to change anything? Probably not. At infinity, considering there's an x squared right next to it, is minus 3x plus 5 really going to change much? Probably not. So essentially what we're left with then is the limit as x goes to infinity for square root of 9x to the 4th over x squared. Well, that can simplify. That's the limit as x goes to infinity for 3x squared over x squared. Oh, well, look at that. It's 3. Ta-da! Okay, the line y equals 5 is a horizontal asymptote to the graph of which of the following functions? So remember, horizontal asymptote. I want 5 to be the limit as x goes to infinity. So I'm going to look at each one of these and see which one would have a limit at infinity of 5. So if I look at A, I've got a trig function over a just polynomial linear function. So it's something that wasn't on a previous slide, but polynomials will also beat out trig functions because trig functions are always between -1 and 1. They're not going to really say much at infinity. So that means the bottom wins. So this one's going to 0. So that's not my answer. Y equals 5x. Well, as x gets bigger and bigger and bigger, isn't that just going to get bigger and bigger and bigger? That one goes out to infinity. 1 over x minus 5. The bottom wins. So that's just like A. This one's going to go to 0. Okay, for D, the coefficient on top matches the coefficient on the exponent on top matches the exponent on the bottom, right? I've got x over x essentially. So I'm going to take the ratio of their coefficients. So that's 5 over -1. That's -5. Close, but not quite what I'm looking for. Okay, now E, the degree on top matches the degree on bottom again. I've got x squared over x squared, so I'm going to take the coefficient, 20 over 4. That is 5. That's exactly what I'm looking for. Perfect. All right, let's move into some indeterminate form. We got L'Hopital's rule that shows up when we've got 0 over 0, or if we've got infinity over infinity, which that just doesn't look like infinity at all anymore. There we go. That's close enough. What we're going to do is we're going to take the derivative of the top and take the derivative of the bottom. They like to do this with functions defined as integrals on the FRQs. In the multiple choice, it usually just turns to be functions. Not quite as complicated. So this one, if I plug in 0, I'm going to get 0 minus 0 on top, 0 plus 0 on bottom. Okay, that's perfect for L'Hopital's rule. So I'm going to take the limit as x goes to 0. Take the derivative on top. The derivative of 7x is 7. The derivative of negative sine x is minus cosine x. Over the derivative of x squared is 2x. The derivative of sine of 3x, we got to use some chain rule on that, is 3 cosine of 3x. Now I can plug in 0. On top I'm going to get 7 minus 1. On bottom I'm going to get 0 plus 3. That's 6 over 3, and we know 6 divided by 3 is just 2. Perfect. Okay, so we've got this one. This one has one of those it's defined as an integral thing. I'm going to save that for our integrals video later when we talk about taking the derivative of integrals, just because I want to talk about it more in context. So let's talk about composite limits. It's when we take the limit of a composite function. So we've got like something like f of g of x. So let me write that. Now this is going to sound a little weird, but basically what we're going to do is bring the limit inside, like this. And let's say that the limit as x goes to g of x, as x goes to a for g of x is like, I don't know, y. Then this will be the limit, let's make that b instead, as x goes to b for just f of x. So if this limit here is just b, then that turns our limit into the limit as x goes to b for just f of x. So little strange, but not too terrible. So this one's got a good example of it. We're going to do the limit as x goes to 1 for f of g of x. So what we're going to do is we're going to bring that limit inside. So it's going to be f of the limit as x goes to 1 for g of x. Well, let's look at this. As x goes to 1, the y value's going to 2 from the left, and it's going to 2 when you come in from the right. So that would mean that it's coming to 2. And this is a little bit more nuanced thing. It comes up this deep sometimes, not too often, but if you look at the arrows, they're both coming to 2 like this. They're both coming to 2 from values below 2. So that means our limit is going to be the limit as x goes to 2 from numbers below 2. So this turned into a one-sided limit for f of x. Well, as x goes to 2 from the left, we're going to 3. So this is just 3, which is c. So the only weird thing came in was it turned into a one-sided limit because g was coming from below 2 on both sides of x equals 1. Okay, the intermediate value theorem comes up a lot. It justifies the existence of a function value. It's very common on FRQs. It'll come up on some multiple choice as well. Big thing, if it's on an FRQ, you must state that the function of interest is continuous and that the value of interest is between the endpoints. That's the hypothesis of the intermediate value theorem. So if your function is continuous and you have 2 endpoints, you're going to get every y value between them. It's just, you just have to say that. You know it in your head, and that's why you come to the conclusion you do. Just put it on the paper. So let's see an example of it. This is a multiple choice of it. We've got let f be a function that is continuous on the closed interval 2 to 4 with f of 2 equals 10 and f of 4 equals 20. Which of the following is guaranteed by the intermediate value theorem? Before I even look at the answer choices, I'm going to think to myself, the intermediate value theorem, since this is a continuous function, tells me that I will get every y value between 10 and 20 on this interval. So keeping that in mind, let's look at the answer choices. A, f of x equals 13 has at least one solution in the open interval. 13 is between 10 and 20. I agree with that. That's more than likely the answer. Let's double check the other ones just to be sure to see why they're wrong. F of 3 equals 15. No. Maybe, but I can't say. The intermediate value theorem only says that at some point in this interval, I will get 15. F attains a maximum. The intermediate value theorem says nothing about maximum. F prime, stop there. Intermediate value theorem says nothing about the derivative. F prime, again, says nothing about the derivative. Okay, A must be correct, which we were already pretty sure of, but now we just got that little confirmation that we wanted. Okay, we've got Rochelle riding a stationary bicycle. The number of rotations per minute of the wheel of the stationary bicycle at time t minutes during Rochelle's ride is modeled by a differentiable function r on the interval 0 to 9. Values of r of t for selected values of t are shown in the table above. Is there a time t for 3 less than equal t less than equal 5 at which r of t is 106 rotations per minute? Justify your answer. Okay, so I'm showing the existence of some function value. Is r of t ever equal to 106? That's why I know I'm going to use the intermediate value theorem. So remember, I need to state that it's continuous, and I need to say that the endpoints are that this value 106 is between the endpoints. So right here, that's how I know the function is continuous, because if it's differentiable on that interval, it must be continuous on that interval. So I know that r of t is continuous on this interval. I also know that r of 5 is 112, r of 3 is 95. So since r of 3 equals 95 and r of 5 equals 112, r of 3 is less than or equal to 106, less than or equal to r of 5. So yes. That's it. I didn't really write that grammatically very well, but the idea is say it's continuous, say that the endpoints, say that the value is in between the endpoints, and actually answer the question. Just writing the reasoning is, you're going to lose a point, and that's going to be silly. You know the answer because you justified it. Actually make sure you answer the question. Okay, let's look at some continuity ideas. The two most common questions are, what value of k make the function continuous at something? And is f of x continuous at x equals ... The big thing on that second one, you have to consider the left and right hand limits if it's a piecewise function. You can't just say the limit is this. That's not enough. You have to consider both sides to justify that the limit exists. So let's look at this. The graph of the function f is shown in the figure above. For how many values of x in the open interval is f discontinuous? Okay, I see a hole here. I see a jump here. I see a removable here. That looks like it's it. So 3. Probably a big thing that they're expecting you to do is count the cusp. Remember, cusps are only places where a function is not differentiable. We've only got 3 points of discontinuity. Cool. Let f be the function defined above. For what value of k is f continuous at x equals 2? So basically, for this piecewise function, we need these two things to be the same when x equals 2. So I need 2x plus 1, x minus 2 over x minus 2. I essentially need to take the limit as x goes to 2 for this. I'm going to squeeze this in here because I didn't leave much room. Well, I can see that I've got a factor of x minus 2 on the top and bottom that can cancel out. So this becomes the limit as x goes to 2 of just 2x plus 1. Well, that's 5. So I need 5 to be equal to k. Oh, okay, cool, I got it. Sometimes that's a little trickier because they'll say like 2k plus 3 or kx or something like that. Just remember, you're at x equals 2, so you can plug in the x values. And otherwise, you'll just have a little bit of algebra to do. This problem was a little more generous. Didn't have as much work. Okay, the graph of the piecewise defined function f is shown in the figure above. The graph has a vertical tangent at x equals -2 and horizontal tangent lines at x equals 3 and x equals -1. What are all values of x at which f is continuous but not differentiable? Okay, so we need continuous. That means x equals 0 is out. It's not differentiable there, but we said that we wanted continuous only. So we're looking for places where it's continuous, but it's also a corner, cusp, or vertical tangent line. And it's at x equals -2. We've got a vertical tangent. And then we see a corner right here. So that looks like x equals -2 and x equals 1. Those are places where it's continuous but not differentiable. Okay, I believe this is our last question. The function f is defined by f of x equals square root of 25 minus x squared for -5 to 5. Let g be this function. And it wants to know, is g continuous at x equals -3? Use the definition of continuity to explain your answer. They were really nice. They even told you what to do. Usually they just say justify your answer, or they'll, even worse, they'll just say is it? And you need to justify your answer because how else would you know? So the first thing we're going to do is prove that the limit at -3 is the same for both f of x and x plus 7. So let's take the left-hand limit. So the left-hand limit, I'm going to be in f of x because that's for numbers less than it. That's going to be the square root of 25 minus 3, negative 3 squared is 9. So square root is 16, so 4. Okay? Now we're going to look at the limit as x goes to negative 3 from the right, and that's going to be for x plus 7. And that's negative 3 plus 7, which is 4. Okay, so it appears the limit as x goes to negative 3 for g of x is 4. Okay, so far so good. Next thing I need to do is I need to show that the function value exists. And right here we can see that less than or equal to means that it's going to exist. I'm assuming that I can plug negative 3 in. So if I plug negative 3 in, that's the square root of 25 minus negative 3 squared again. That's 25 minus 9, which is 4. Okay, last thing I got to do is just say the limit as x goes to negative 3 is equal to g of negative 3. So just like before, we've done all this justification. Wouldn't it be a shame if we didn't actually answer the question, which is g continuous? Yes, it's continuous. And I ran out of room. Isn't that a beautiful song where I'd shove continuous up against the wall? Okay, long video, but we got lots of good work in this. Look out for the next one shortly on derivatives. Keep rambling, making the video longer.